So this is an introductory video into the Environmental Science Unit 4 Outcome 2, and we're looking at, is climate predictable? So the Earth's atmosphere is made up of layers. The troposphere is 0 to 12 kilometres, so 12 kilometres away from the Earth's surface on average. And that goes up until a boundary layer here, which is the tropopause. Past that is the stratosphere, which is 12 to 50 kilometres. And outside of this is the stratopause. Outside of this is the mesosphere, which is 50 to 80 kilometres. Again, with a mesopause through here. And then there's the thermosphere extending beyond that. So the temperature, the densities of the gases within these different layers, as well as the concentration of gases, is what creates this formation of layers. So in the troposphere, the temperature is on average 15 degrees Celsius. The tropopause, which is this boundary layer again here, is about minus 55 degrees Celsius. We go back out into the stratosphere, and by the time we hit the stratopause, we're back at freezing point, or 0 degrees Celsius. And then the mesopause, which is this next layer out here, is minus 100 degrees Celsius. Past here, we do start to heat up again. So you can see the temperature kind of from the troposphere going out starts reasonably low, and then cools down, warms back up, cools down again, and warms back up. So you can see again this temperature line that's being mapped out on this graph. So the temperature down the bottom on the x-axis is in Kelvin, and the altitude on the y-axis as we're going up into those different atmospheric layers. So what do we need to know? We need to know that most of our gases happen within the first 30 kilometres. So that's only this stretch here that we really look at these gases occurring, and then we focus on. So we have nitrogen existing as N2 at about 780 parts per million. We've got oxygen, O2, which is about 209 parts per million. 209,000 parts per million. We've got argon, which is only 9,000 parts per million. And funnily enough, CO2, or carbon dioxide, that we hear so much about with our climate crisis, actually is only about 350 parts per million, which is not a high concentration. The other thing we need to remember is our inert gases. So these are gases that exist in a much lower concentration. And these gases are methane, hydrogen, which exists as a molecule. We have nitrous oxides, which we write as NOx. And we also have carbon monoxide. So monoxide being where we only have one oxygen per carbon as opposed to two oxygens per carbon like we do in carbon dioxide. O3, which is ozone. And really the most important one is water. So water vapor is one of our biggest interferences with the sun's radiation reaching the Earth's surface. It provides an opportunity for these other particles to kind of form together. You know, these other smaller inert gases form the nucleus of these bigger particles, and the water vapor actually clings onto those and creates bigger particles and way more interference. So O3, or ozone, also is our ozone layer. So that's just above the tropopause. That's in the first couple of kilometres of the stratosphere. And it actually creates a blanketing effect for us, blanketing both the warmth in and a bit of the nastier solar radiation out. So what we need to remember is that all of these air particles, which include things like pollen and dust and other natural particles, they actually move in cells within our atmosphere. So our air is always moving, and that's why we get high and low air pressure systems as well as wind. So at the equator where it's hottest, gas will rise. It will travel to where it is cooled, and when it is cooled, it will fall back down to the earth due to its density, and then it will travel back to the equator being pushed around in this cell. This also happens up in the kind of Mediterranean areas or north of the tropics. And we also look at these again happening in the polar circle. So they'll always rotate the same way because of the way that heating and cooling happens. The other thing we need to know is that we have northeasterly trade winds and southeasterly trade winds, and that's due to the rotation of the Earth. Kind of like a lag effect, so the turbulence on a ball, if you will, if you were spinning it on your finger. We also look at the cycles of the Earth's climate within this sequence. And we look at solar cycles, which a lot of people attribute a lot of our climate change realities to. So what happens in a solar cycle is the sun actually shifts polarity based on the concentration of gases being at different poles. So the way that this happens, this actually results in more heat being closer to the Earth and therefore having this waving effect. These polar cycles actually happen reasonably often at about 11 years. So we do see these types of intermittent cycles, which again, we need to look at and consider as one of our things within our climate change series that this sequence leads on to. Another cycle that exists in the Earth is the Milankovitch cycles. So we look at eccentricity, obliquity, and precession. So what is eccentricity? Eccentricity is the orbit in which the Earth moves around the sun. So it actually expands and contracts from an ellipse to almost a perfect circle. And this still spins on its axis through here. So this happens on about 100,000 year scale, which also describes some of our climate differences that we do see. Next, we talk about obliquity. So if we take the Earth's axis, or if we skewered the Earth on the axis that it rotates on, it would be this north-south line here. And what we talk about with obliquity is the ability for this north-south pole to move. If the north is moving to the left, the south is moving to the right, and we actually rotate on this center point as a pin, and we pull that axis in as one of our other cycles. That's obliquity. Next, we talk about precession. So again, in reference to that axis, which is this one running through here, we think about that degrees from vertical. So now if you think of the Earth like a spinning top that's pictured on the right here, you can see the base here will always stay the same. It will try to spin from the same point at the bottom. What happens is this yaws from side to side, really kind of in a circular motion, and this is what we call the precession, and this also has a cycle. We also talk about the albedo effect within this sequence. So the albedo effect is the reflectance of the Earth. This doesn't always have to be the Earth's surface like is pictured here. We can actually also talk about cloud cover as well as having an albedo effect, and cloud cover is of course water vapor. So what is the albedo? The albedo effect is the ability for snow to reflect the sun's energy back off. So if we look at this left-hand side here, we've got 70% absorption on areas like dry dirt. We've got an 80% absorption over here on the greener grass, and we've got about a 90% absorption by the water body that we can see down in this section. Conversely, we look at a winter portrait of the same place, and we're looking at 80 to 90% reflected all the time. So that's from the sun here, and that's straight off of the Earth's surface because it is covered by snow. we've only got about 10 to 15% absorption, which is when the snow would melt and all the heat energy that gets trapped in there. So the albedo effect is how reflective the Earth is. We use this knowledge that we've just gone through to look at the greenhouse effect. So the greenhouse effect is a natural phenomenon. It was there before we did anything to alter it. So what happens to the greenhouse effect when we start to add these other gases is that it's enhanced. So there's a difference between the greenhouse effect and the enhanced greenhouse effect. So within the 1700s, there was an industrial revolution which led to combustion engines. It also led to vegetation clearance, which meant that we had fewer natural sinks for our carbon, such as trees. And we also increased our cropland, which, if you think back to that albedo slide just a second ago, that dry land actually absorbs way more heat and doesn't reflect any of it back out, which means our surface is getting a bit warmer. The other thing is we increase chlorofluorocarbons, or CFCs, and hydrochlorofluorocarbons, which is HCFCs. We've also got an increase in how intense our ozone layer is because of the trapping of these things. And these are due to refrigeration, combustion engines, and other such things that began in the Industrial Revolution. So when we think about greenhouse gases, we think about them in comparison to carbon always. So we think about their capacity to absorb heat in comparison to carbon. We think about their persistence in the atmosphere, so how long they stay in the atmosphere in comparison to carbon, and also the concentration of them in comparison to carbon, remembering that the carbon dioxide is actually quite low when we looked at that greenhouse gas concentrations earlier on. The other thing that I find really important to note is that this is not a global warming phenomena. It's actually a climate change phenomena. While overall the Earth's average temperature is increasing, it's actually creating more freak storm events, ocean acidification, and those kinds of things. So we actually lump them all in together and call it climate change as opposed to global warming. It's just a way more encompassing way to discuss the effect that it's having on the Earth. So that's just a beginning understanding of what I'm bringing to the table as my understanding at the start of this teaching sequence. And these are just some of our greenhouse gases, again, naturally occurring, but really an important role in our greenhouse effect and how that affects climate change.